तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the second lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, we shall study about the design for shear. First, we shall study about the limit state of collapse for shear. Next, we shall move on to maximum permissible shear stress. Then, we shall move on to design of transverse reinforcement, and finally, we shall look into the detailing requirements for shear. First, limit state of collapse for shear. Last time, I mentioned that when we study shear, we study the strength at ultimate. We do not use the principles of compatibility of strains or the constitutive relationships of the stress-strain behavior in concrete or steel. We use an equilibrium equation, and that equilibrium equation is based on the ultimate strength of the concrete under flexural shear. Based on this concept that the total shear capacity of the section is based on the summation of the capacity of concrete and that of steel, we write the expression for the ultimate shear capacity of a section. The ultimate resistance of a section, which is represented as V subscript UR, consists of a concrete contribution Vc and the stirrup contribution Vs. Thus, VUR is equal to Vc plus Vs. Here, Vc includes Vcz, which is the contribution from uncracked concrete, then Va, which is the aggregate interlock, and Vd, which is the dowel action. The last time, when we studied the components of shear resistance, we found that for a prestressed concrete section, the components of shear resistance are Vcz, Va, Vd, then Vs, and if the tendon is inclined, then we get a vertical component of the prestressing force, which is represented as Vp. Now, three of these components are grouped together under the contribution of concrete, which is represented as Vc. Thus, now we are having in all three components, one is Vc, another is Vs, and when the tendon is inclined, we include Vp. In general, VUR is equal to Vc plus Vs, and the value of Vc depends on whether the section is cracked due to flexure or not. Section 22.4 of IS 1343-1980 gives two expressions of Vc, one for cracked section and the other for uncracked section. Last time we had studied that when the concrete member is loaded, first the flexural cracks are initiated, next the flexural cracks tend to become flexure shear cracks as we move out from the midspan, and then we may find some web shear cracks developing near the supports. The shear strength of concrete depends whether the section has cracked or not. The code says that we need to calculate the shear capacity of concrete from two expressions. One expression is given for the cracked section, the other expression is given for an uncracked section. Both the expressions need to be evaluated at a particular section. The lower value obtained from the two expressions is selected. Usually, the expression for the uncracked section will govern near the support. The expression for the cracked section will govern near the midspan. Usually, for a beam under uniformly distributed load, cracks are generated near midspan earlier, and in that region it is the expression for the uncracked section which will govern, whereas the portions near the support, their cracks develop at a much later stage, and usually the expression for uncracked section will govern in that region. Next, we are moving on to the expressions for the VC for the two types. For an uncracked section, VC is equal to VC0, where the VC0 is expressed as 0.67 BD times root over FT square plus 0.8 times FCP times FT. VC0 is the shear causing web shear cracking at CGC. Thus, the capacity of concrete for an uncracked section is the value of shear which causes a web shear cracking near the support, and this expression can be derived from the concept of bone circle. In this expression, B is equal to breadth of the section, which is equal to BW, the breadth of the web for flange sections. D is the total depth of the section, which we have represented as H in earlier occasions. Ft is the tensile strength of concrete, which is 0.24 root FCK. This is the direct tensile strength. FCP is the compressive stress in concrete at CGC due to the pre-stress, which is equal to PE by A, and we are just taking the numeric value of FCP. Actually, FCP is compressive, but we are taking only the numeric value of FCP in the expression, and FCP is equal to PE, the effective pre-stress, divided by the area of the cross section. The previous equation can be derived based on the expression of the principal tensile stress sigma 1 at CGC. If we take an element at the CGC, then there is a shear stresses and there is a compressive stress, which is FCP, which is given as PE by A. Now, this state of two-dimensional stresses can be decomposed to a state of principal stresses. I would say it can be transformed to a state of principal stresses, where sigma 1 is the principal tensile stress and sigma 2 is the principal compressive stress. If we plot these two stresses in the Morse circle, then we find that the point describing the state of stress is given by this point, where the point corresponds to the vertical surface with a compressive stress of minus FCP and a shear stress of V, whereas the horizontal surface is given by the point lying on the vertical axis, where there is no normal stress, but there is shear stress of V. From this, we can find out the expression of sigma 1, which is the principal tensile stress, and observe that the value of sigma 1 is much smaller than the magnitude of sigma 2. This is the case when there is a prestressing force in a section. The value of sigma 1 can be calculated if we are able to locate the origin of the circle. The origin of the circle is at minus half FCP by 2, that means it is the x coordinate is half of the coordinate of this point and the y coordinate is 0. Sigma 1 is given as the distance from the origin. Now, the distance from the origin is the radius of the circle, and that can be found out as minus half of FCP by 2 square plus V square. The full is taken as a square root. Thus, the principal tensile stress is equated to the direct tensile strength of concrete. Sigma 1, to repeat, is equal to minus FCP by 2, which is the location of the origin of the circle, plus the radius of the circle, which is the square root of FCP by 2, which is equal to FCP square by 4 plus V square, and we can substitute the expression of V, which is given as Vc0, the shear corresponding to the initiation of a web shear crack, times Q divided by IB. We shall explain these terms in the next slide. Here we have written the expression of sigma 1 from the Mohr circle, and we are equating that expression to Ft, which is the direct tensile strength of concrete. In this previous equation, the I is the gross moment of inertia, Q is the product of the area above the CGC times the vertical distance of the centroid of that area from CGC. That means Q is equal to AT times Y tilde, where AT is the area of section above CGC and Y tilde is the vertical distance of the centroid of AT from CGC. The shear stress at CGC is equal to Vc0 times Q divided by IB. This expression we learn from basic structural mechanics. That means once we have substituted the expression of the shear stress in terms of the shear force, next we can transpose the terms to get the expression of the shear force which initiates a web shear crack at the CGC. Transposing the terms, Vc0 is equal to IB divided by Q times root over Ft square plus FCP times Ft. That means from the previous equation, by transposing the terms, we get an expression of Vc0 in terms of the sectional properties of the section, which are I, B and Q. Then we also have the tensile strength of the concrete in the terms of Ft, and we have the amount of prestressing force taken into account through the term of FCP. Here we can note that if FCP is increased, that means if the prestressing force is increased, the shear corresponding to the initiation of web shear crack also increases. Thus, here we are utilizing the benefit of the prestressing force in increasing the shear capacity of the section. This exact expression is substituted by a simpler expression, which is 0.67 times BD. This represents the IB by Q for a section. It is an exact substitution for a rectangular section, but it is a conservative substitution for other types of sections. That means the code gives us a simpler expression of IB by Q, which is generic for any type of section, and that is 0.67 times BD. Note another change, that we have substituted FCP by 0.8 FCP. The reason is, to be conservative, only 80% of the prestressing force is considered in the term 0.8 FCP. Thus, instead of taking the full prestressing force, to be conservative, the expression in the code considers only 80% of the prestressing force, prestress at the level of CGC. Thus, we have derived the expression of the shear force that causes web shear cracks near the supports of a section. For a flange section, when the CGC is in the flange, the intersection of web and flange is considered to be the critical location. The expression that we have derived earlier is based on the stress at the level of CGC being equal to the tensile strength of concrete, the principal stress being equal to the tensile strength of concrete. But for a flange section, the cracking may occur at the junction of the web and the flange when the CGC lies in the flange. Hence, the code recommends that for a flange section, apply the expression for the location which is at the junction of the web and the flange, and substitute 0.8 FCP by the term 0.8 times the stress in concrete at the level of the intersection of web and flange. This stress can be found out by the elastic analysis that we had seen under the analysis of sections for flexure, and we can use the same expression as before for the shear causing web shear cracks, but we are substituting 0.8 FCP by 0.8 times the stress at the level of the intersection of the web and the flange. In presence of inclined tendons or vertical prestress, the vertical component of the prestressing force Vp can be added to Vc0. Thus, the code says that we can add Vp to Vc0 and the total strength can be considered as 0.67 BD root over Ft square plus 0.8 times FCP times Ft. This full thing is the shear causing the web shear cracks plus Vp, which is the vertical component of the prestressing force for an inclined tendon. Next, we are studying the expression of Vc for a cracked section. This expression is more involved because the cracking of concrete is inherently variable in nature, and the cracks are first generated due to flexure and then they propagate due to shear. In the expression of the code, Vc is equated to Vcr, where Vcr is the shear corresponding to flexure shear cracking. The earlier term Vc0 was for web shear cracking, whereas Vcr is for flexure shear cracking. Vcr is equal to, within bracket, 1 minus 0.55 times FPE divided by FPK times tau C BD plus M0 times V divided by M. The code says that VCR need not be less than 0.1 times BD to the power FCK. Now, in this expression, there are two terms. One term on the left, this is the additional shear that changes a flexural crack to a flexure shear crack. That means VCR has two components. The first component is the additional shear that changes a flexural crack to a flexure shear crack, and the second term M0V by M is the shear corresponding to the generation of a flexural crack at the bottom of the beam. The first expression is an empirical expression, and the notations of these expressions are as follows. FPE is the effective pre-stress in the tendon after all losses, and it should be less than or equal to 0.6 FPK. Tau C is the ultimate shear stress capacity of concrete, which is obtained from table 6 of IS 1343-1980. The values of tau C are plotted in this graph. It is given in terms of the amount of pre-stressing steel. The graphs are given for two grades of concrete, M30 and M40. We observe that as the amount of pre-stressing steel is increasing, the strength of the concrete is also increasing, but it gradually tapers off to a steady value. There is not much difference between the two grades of concrete, and from this we can infer that in fact the strength of the concrete under shear, even for a cracked section, increases with amount of the pre-stressing steel. Last time we have found that for a pre-stressed section, even for the cracked region, since the pre-stressing steel applies a compression, the growth of crack is reduced, the zone of concrete under compression is increased, the aggregate interlock is increased, the bond between the longitudinal steel and concrete is relatively retained better, and hence dowel action is retained, and hence the strength of the concrete under shear for a cracked section increases with the amount of pre-stressing steel. In the expression, B is the breadth of the section, which is equal to BW for a flange section, which is the breadth of the web, and D is the distance from the extreme compression fiber to the centroid of the tendons at the section considered. The second term, M0V by M, is the shear corresponding to the moment M0 that decompresses or nullifies the effect of pre-stress at the tension phase and initiates a flexural crack. What I had said before, that the second part of VCR is the shear corresponding to the initiation of a flexural crack at the bottom face. Now, that shear is given as the ratio of the shear which causes a decompression at the tension phase, and that expression is given as 0.8 FPT times I divided by Y. Thus, in this expression, M0 by M is a ratio of moments, and hence it is a expression without any units. This times V is the amount of shear that causes a flexural crack at the bottom of the beam. Now, how did we get this expression of m0 is equal to 0.8 fpt times I by y? This expression is actually 80% of the moment that causes decompression at the level of CGS. To recollect, m0 is the moment corresponding to the decompression of the tension phase, which generates the flexural crack, and fpt times I by y is the moment corresponding to the decompression of the concrete at the level of the CGS. m0 is taken as 80% of that moment which causes decompression at the level of CGS. In this expression, fpt is the compressive stress in concrete at the level of CGS due to prestress only. An equal amount of tensile stress is required to decompress the level of CGS. Thus, if we calculate the compressive stress in concrete at the level of CGS, we can find out what is the moment which will generate an equal and opposite tensile stress at the level of CGS, which will thus decompress the concrete at the level of CGS. Now, corresponding to that moment, if we take 80% of that, that will give me the moment which will decompress the tension phase, which is below the level of CGS. In the expression of m0, y is the depth of CGS from CGC. The factor 0.8 implies that m0 is estimated to be 80% of the moment that decompresses the concrete at the level of CGS. From this, we get the expression m0 is equal to 0.8 times fpt, which is the compressive stress in concrete at the level of CGS, times I by y, where y is the distance of the CGS from CGC. Thus, it is an inverse calculation that if we are able to calculate the stress at the level of CGS, we can find out the moment causing decompression at the level of CGS, and 80% of this moment is considered to decompress the tension phase and thus generate the flexural crack at the tension phase. Now, the shear corresponding to this generation of the flexural crack at the tension phase is given as m0 divided by m, where m is the moment due to service loads, times V, which is the shear due to service loads at a particular section. Since m0 by m is a ratio, the quantity m0 by m times V has the unit of shear, and that is the shear which is an estimate of the shear causing a flexural crack at the bottom. Since the concrete is cracked and the inclination of tendon is small away from the supports, any vertical component of the prestressing force is not added to VCR. Earlier we had seen that the code allows us to incorporate Vp along with Vc0, which is the shear causing web shear cracking. But here we find that the code does not allow us to include Vp with VCR, which is the shear corresponding to flexure shear cracking. The reason is, after cracking, the effect of prestressing is small, and anyhow for a simply supported beam, the inclination of the tendon is small near the midspan, and hence the contribution of Vp is negligible, and we did not have to include Vp and club it with FCR. Next, let us learn the maximum permissible shear stress in concrete. As I told you last time that there are several modes of shear failure. The approach in shear design is that we design the reinforcement based on the ultimate strength of the concrete to take shear. We also do some other checks and detailing requirements to avoid other modes of failure. The maximum permissible shear stress in concrete is one way to check the crushing of concrete in shear compression failure. To check the crushing of concrete in shear compression failure, the shear stress is limited to a maximum value which is represented as tau c max. The value of tau c max depends on the grade of concrete and is given in Table 7 of IS 1343-1980. Thus, Vu divided by B times dt should be less than tau c max. That is, whatever is the loading, the shear stress that comes in the section should be less than the maximum permissible shear stress in the concrete. This is to avoid a sudden shear compression failure. In this expression, B is the breadth of the section, dt is the greater of dp or ds, where dp is the depth of CGS from the extreme compression fiber and ds is depth of centroid of regular steel. Vu is the shear force at a section due to ultimate loads. Thus, whenever we are doing this shear check, we are calculating the average shear stress based on the depth which is larger of the depth of the CGS and the depth of the non-prestressed steel. This larger value is denoted as dt. Vu divided by B times dt should be less than or equal to tau c max. The tau c max is given in the form of a table, and when it is plotted, it looks like this, that for different grades of concrete, the tau c max slightly increases and more or less it stabilizes when we reach a concrete strength of 60 Newton per millimeter square. To check web crushing failure, the Indian Roads Congress Code IRC 18-2000 specifies a minimum thickness of the web for T sections. In the clause 9.3.1.1, the minimum thickness is 200 millimeters plus diameter of the duct hole. In the Indian Road Congress Code, to check the web crushing failure which occurs for a flange section with thin webs, the code specifies a minimum thickness of the web, and that is equal to 200 millimeters plus the diameter of the duct. This provision is of course not there in IS 1343-1980, but it is advisable to maintain a minimum width of the flange to avoid web crushing failure for our flange section. Next, let us look into the design of transverse reinforcement in more details. When the shear demand Vu exceeds the shear capacity of concrete, which is denoted as Vc, transverse reinforcements in the form of stirrups are required. The stirrups resist the propagation of diagonal cracks, thus checking diagonal tension failure and shear tension failure. The main purpose of the stirrups is to check the diagonal tension failure which occurs when a diagonal crack propagates rapidly through a section, depth of the section, and also the stirrups should check the shear tension failure. In a shear tension failure, the diagonal crack merges with an horizontal crack at the level of the bottom steel, and the crack propagates towards the support and the longitudinal steel loses its anchorage. To resist both these types of failure, we need shear reinforcement which will traverse the diagonal cracks. The stirrup resists a failure due to shear by several ways. The functions of stirrups are listed below. First, stirrups resist part of the applied shear, which is denoted as Vs. Second, they restrict the growth of diagonal cracks. Third, the stirrups counteracts widening of the diagonal cracks, thus maintaining aggregate interlock to a certain extent. Fourth, the splitting of concrete cover is restrained by the stirrups by reducing dowel forces in the longitudinal bars. Thus, the contribution of stirrups is not only in Vs, but it has a contribution in Vc as well. When there are stirrups, the propagation of the diagonal cracks is checked, the opening of the diagonal cracks is reduced, thus increasing the aggregate interlock, and also the dowel forces in the longitudinal steel is reduced, and hence the dowel action is retained. Thus, for this different reason, stirrups are mandatory for a reinforced concrete or a prestressed concrete beam. After cracking, the beam is viewed as a plain truss. The top chord and the diagonals are made of concrete struts. The bottom chord and the verticals are made up of steel reinforcement ties. Based on this truss analogy, the total area of the legs of stirrups, which is represented as ASV, is given as follows. In order to find out the amount of steel which is needed to provide the shear strength, the concept of truss analogy is used. In this truss analogy, after the cracking of concrete, the concrete under compression form diagonal struts, and the vertical stirrups form the ties, and the top chord is a compression chord, and the bottom longitudinal steel acts as the bottom tensile chord. This truss action is used to develop the expression of the amount of steel that is needed to resist the shear strength. The expression is given as follows: ASV divided by SV is equal to VU minus VC divided by 0.87 Fy times dt. VU is the shear demand. From this, we are subtracting the concrete contribution, which is Vc, which we can calculate for a particular section from the expressions of VCR or VC0. Whichever is lower, we take as the expression of Vc. Subtracting the Vc from Vu, we get the value of Vs, and then from the truss analogy concept, we can write the amount of steel and the spacing by an expression which is ASV divided by SV is equal to Vu minus Vc, which is Vs, divided by the maximum stress in the stirrups, which is 0.87 times the characteristic yield stress, times dt, which is the effective depth up to the higher of the CGS, or it's the effective depth which is larger of the depth of the CGS and the depth of the longitudinal steel. We are not going into the details of the truss analogy here, but it is advisable to remember that this expression is based on a truss analogy concept, and the angle of inclination of the cracks is considered to be 45 degree. The notations in this previous equations are as follows. SV is the spacing of the stirrups, dt is greater of dp or ds, where dp is the depth of CGS from the extreme compression fiber and ds is the depth of centroid of regular steel. Fy is the yield stress of the stirrups, which is reduced to 0.87 Fy. The grade of steel for stirrups should be restricted to Fe 415 or lower. That means the code does not allow a grade of steel greater than Fe 415 because such grade of steel does have less yielding, and hence the code restricts the grade of steel to be used for stirrups. For the design, if Vu is less than Vc, theoretically we do not need stirrups, but the code says that we have to provide a minimum amount of transverse reinforcement, which is based on the equation ASV divided by B times SV is equal to 0.4 divided by 0.87 Fy. This equation is derived by assuming that the stirrups should have a minimum stress of 0.4 Newton per millimeter square, and this is the expression which gives the minimum amount of transverse reinforcement. Here also B is the breadth of the section, which is equal to BW for the breadth of the web for flange section. If Vu is less than half of Vc and the member is of minor importance, stirrups may not be provided. That means the code gives us some freedom that if the shear demand is half of the shear capacity of concrete and the member is of minor importance, in that situation we may not provide stirrups, but otherwise we have to provide stirrups. If Vu is less than Vc, we have to provide the minimum amount of stirrups. Next, let's look at the detailing requirements for shear. The detailing requirements for the stirrups in IS 1343-1980 are briefly mentioned. The maximum spacing of stirrups is given. The spacing of stirrups is restricted so that a diagonal crack is intercepted by at least one stirrup. So in the cross section, the notations are dp is the depth of the CGS, ds is the depth of the longitudinal steel, bw is the breadth of the web, and h is the total depth. SV is the spacing of the stirrups which we are seeing in the elevation of the beam. The spacing is restricted because there should be at least one stirrup intercepting a diagonal crack, and the maximum spacing is given in clause 22.4.3.2. It is equal to 0.75 times dt or 4 times bw, whichever is smaller. Thus, the maximum spacing is the smaller value of 75% of the value of dt or 4 times the breadth of the web. If the shear demand is high, that if it crosses 1.8 times Vc, then the maximum spacing is reduced to 0.5 dt. Thus, for higher values of Vu, the stirrup spacing is even restricted. The variables are Bw is the breadth of the web, dt is greater of dp or ds, dp is the depth of CGC from extreme compression fiber, ds is depth of centroid of non-prestressed steel, Vu is the shear force at a section due to ultimate loads, Vc is the shear capacity of concrete which we determine from Vc0 or Vcr. A minimum amount of stirrups is necessary to restrict the growth of diagonal cracks and subsequent shear failure. As per clause 18.6.3.2, stirrups are recommended for beams with thin webs, and the minimum amount of stirrups is given in terms of AWH, the horizontal sectional area of the web in plan. That means there is an additional requirement for the minimum amount of stirrups for beams with thin webs, and that is given in terms of a horizontal sectional area of the web. This area is shown in this figure, that if we take a horizontal section, then AWH is the area of the web for this horizontal section. In presence of dynamic loads, ASV minimum is equal to 0.3% of AWH, which can be lowered to 0.2% AWH when H is less than or equal to 4 times BW. With high strength bars, ASV minimum is equal to 0.2% AWH, which can be lowered to 0.15% AWH when H is less than or equal to 4 times BW. In absence of dynamic load, when H is greater than 4 times BW, then ASV minimum is equal to 0.1% of AWH. There is no specification of ASV minimum when H is less than or equal to 4 times BW. Thus, we find that there are two requirements of minimum amount of stirrup. One is based on the truss concept, that the stirrups has to take a minimum amount of shear stress, and the other expression is for beams with thin webs, and that is given in terms of the horizontal section of the web. The stirrups should be anchored to develop the yield stress in the vertical legs. This is very important, that we anchor the stirrups properly so that it can develop the yield stress at ultimate. The stirrups should be bent close to the compression and tension surfaces, satisfying the minimum cover. That means the stirrups should run throughout the full depth as much as possible. It should satisfy, of course, the minimum cover requirements, and the stirrups should be bent around the top steel and the bottom steel. Each bend of the stirrups should be around a longitudinal bar. The diameter of the longitudinal bar should not be less than the diameter of the stirrups. In order to maintain the bend in the stirrups, the diameter of the longitudinal bar has to be at least equal to the diameter of the stirrup. The end of the stirrups should be anchored by standard hooks. That means wherever we are ending the stirrups, there should be a standard hook, and these hook specifications are given in the handbooks. There should not be any bend in a re-entrant corner. In a re-entrant corner, the stirrup under tension has the possibility to straighten, thus breaking the cover concrete. Let us understand this by the help of a sketch. The following sketches explain the requirement of avoiding the bend of a stirrup at a re-entrant corner. In a re-entrant corner, if we provide a single stirrup, then the stirrups tend to straighten out and it tends to break the concrete near the re-entrant corner. This detailing is incorrect. The correct detailing is that we have to provide two pieces of stirrups. None of them has a bend near the re-entrant corner, and hence does not pose a threat of breaking the concrete near the re-entrant corner. Today, we studied the design for shear. First, we studied the limit state for shear. As we had said earlier that in the shear analysis and design, we do not consider the complete behavior. The design is based on the ultimate strength of the section under shear. This strength, which is represented as VUR, is a summation of Vc and Vs, where Vc is considered to be the contribution of concrete and Vs is the contribution of the stirrups. In Vc, we are placing all the three individual components of the concrete under compression, which is uncracked, which is represented as VCZ, then the aggregate interlock, which is represented as VA, and the dowel action VD. All these three are clubbed together in the expression of Vc. The code gives us two expressions of Vc, one for a uncracked section and other for a cracked section. The uncracked section expression is usually governs the region near the supports, and the cracked section expression usually governs near the region near the midspan. As we had seen earlier, that when a beam is loaded, first we observe flexural cracks near the midspan, and then the flexural cracks away from the midspan tend to bend due to the effect of shear, which this type of cracks are called flexure shear cracks. And then with further increase in the load, we may have cracks near the centroid of the section close to the supports, and those cracks are inclined, and those cracks are called web shear cracks. Now, the expression for uncracked concrete, the shear strength of concrete is given as the shear force which initiates a web shear crack at the level of CGC. The expression of Vc equal to Vc0 is derived from the concept of Mohr circle of the state of stress at the level of CGC. For a point at the level of CGC, there is a shear stress, and along with that, for a prestressed concrete beam, there is a normal compressive stress, which we are denoting here as FCP. From the values of V and FCP, we can write the expression of the principal tensile stress sigma 1 based on the Mohr circle, and then we equate sigma 1 to the direct tensile strength of concrete, which is denoted as Ft. Once we write this expression and then substitute the shear stress V is equal to the shear force Vc0 times Q divided by IB, we transpose the terms to bring Vc0 on the left hand side. From this, we get an expression of Vc0, which is the shear force that generates a web shear crack at the level of CGC. In this expression, FCP is reduced to 80% to stay conservative. If we have a flange section, then the code recommends that the crack may initiate at the level of the intersection of the web and the flange, and hence 0.8 FCP should be substituted by 0.8 times the stress in the concrete at the level of the intersection of the web and the flange. The second expression for Vc is based on a cracked section, where Vc is equal to Vcr, which consists of two terms. The first term is the shear that propagates a flexural crack to a flexural shear crack. This expression is in terms of the prestressing force FPE and the capacity of concrete, which is given as tau c. The capacity of concrete tau c increases with the amount of prestressing steel, because the more prestressing steel we have a reduced length of the flexure shear cracks, we have more concrete under compression, there will be more aggregate interlock and a better dowel action. Hence, the capacity of concrete is increased with the amount of pre-stressing steel. The second term of VCR is the shear corresponding to the generation of a flexural crack at the bottom of the beam. This is based on the ratio of the moments m0 by m, where m0 is the moment required to generate a flexural crack at the bottom, and m is the moment which is the demand based on the service loads, and V is also the demand based on service loads. We can have both V and M as the demands based on ultimate loads, because the load factors anyhow will cancel out from the numerator and the denominator. M0 V by M denotes the shear which corresponds to the generation of a flexural crack at the bottom of the beam. Thus, VCR consists of two terms. The first term is the shear which extends a flexural shear crack to a flexural shear crack, and the second one is the shear which is needed for the generation of a flexural crack at the bottom of a beam. Now, once we have learned these two expressions of VC0 and VCR, we can calculate Vc as the lower of these two values at any particular section. We can add Vp to Vc if the tendon is inclined, and this is allowed only with the expression of Vc0. Once we have calculated Vc, we can subtract this from Vu, the shear demand, and get the value of Vs. The amount of steel and the spacing is given by an expression which is based on the truss analogy for shear, and this is in terms of Vs and the amount maximum stress that can generate in the stirrups, which is 0.87 times Fy. The code recommends to provide a minimum amount of stirrups even if Vu is less than Vc, and that is based on a certain minimum stress to generate within the stirrups. The code also gives us another expression of minimum amount of stirrups, which is applicable for beams with thin webs, and the values are given for in presence of dynamic loads and in absence of dynamic loads. Next, we studied about the detailing of the stirrups. The stirrups should be properly anchored at the top steel and at the bottom steel. They should traverse the depth as much as possible, satisfying the cover requirements. The spacings of the stirrups is restricted because a diagonal crack should be intercepted by at least one stirrup, and the stirrups should have standard hooks at the ends. The function of the stirrups is multiple. It not only provides the shear capacity Vs, but it also influences Vc by increasing the dowel action, the aggregate interlock, and checking the growth of the crack. Thus, stirrups is recommended for beams even if Vu is less than Vc, and it has to be properly detailed so that it forms the truss action is formed and we are able to check a premature shear failure. There are other detailing requirements which checks the other modes of failure, such as the shear compression failure and the web crushing failure. We have to limit the shear stress to a maximum value so that we do not have any sudden shear failure. In the next class, we shall move on to the design steps for shear. Thank you.